Okay, so as you just all heard, this is being recorded and will be played to YouTube. Just before we start, I'd like to say that if there are any topics you would like to be covered in one of these public talks, whether you'd like to give the talk yourself or you can think of a good speaker or a set of speakers, then please do contact us and we will try to make it happen. So today, I'm very happy to have Dylan Rankin here talking to us about hardware accelerated inference for real-time gravitational wave astronomy. Take it away, Dylan.
Thanks a lot. Yeah, so as Adam just mentioned, so the title of this talk is Hardware Accelerated Inference for Real-Time Gravitational Wave Astronomy. This is based off work that we've been doing for the past, maybe at least a year, if not more, with myself along with collaborators at MIT and Minnesota and Fermilab. And you can find a link to a paper that discusses a lot of the work and the results to that archive link there. So just an outline of what I'll talk about today. I'll give sort of a brief introduction behind our thinking, sort of that led us to this work, and that we think is sort of an impetus for what we need here. We'll talk about the LIGO algorithms that we sort of use to demonstrate this sort of work. The crux of this work then that I'll discuss is related to this sort of paradigm called inference as a service, which we'll come to, and then we'll show some deployment results of this on real workflows, as well as some future work and applications. So this sort of sits in the middle of these sort of three maybe realms of sort of scientific applications or scientific algorithms, computing hardware that's advancing the speed with which we can do these things, as well as AI. I want to sort of clarify that this is not a machine learning talk, so I'm not going to sort of dive too deep into machine learning and AI, even though that's certainly part of the work. But that I think is a much sort of separate thing than what we're talking about here, which I think is much more general. So with that said, the introduction here is that machine learning, regardless of what you think about this, is becoming increasingly popular. I think that's just a fact. And there's certainly many different algorithms that are emerging for gravitational wave data analysis, as well as analysis in all sorts of other sort of fields of science. And I think a lot of these, one of the interesting things is that these AI and ML algorithms are really starting to cover just the full span of analysis workflows. They're starting to cover, to have this real wide range of different architectures that people are interested in for different problems, et cetera. And the sort of crux of this work, and the question that I think this work really answers that is unanswered in a lot of other cases is, okay, so we have all these algorithms, how can we actually deploy them at scale? How can we deploy them easily? How can we deploy them quickly and efficiently? And these are all sort of, I think it's a simple question to ask, and I think the answer is non-trivial, but there is an answer. And this sort of leads us to this toolkit that we've designed, that we've dubbed Heterogeneous Enabled Real-Time Messenger Execution as a Service, or HERMES. So one of the sort of lead-ins to this, why is this maybe particularly interesting, is certainly in the context of multi-messenger astrophysics, or MMA, right? We have this we detect something in LIGO. How can we do a detection of something fast enough that we can alert others to the follow-up? And this sort of fast detection, I think, definitely lends itself to machine learning solutions to problems, and to efficiently executed and quickly executed machine learning solutions, not just effective ones. But this is something that requires, I think, sort of a change in how we think about doing inference and doing algorithmic execution. The two sort of algorithms that we'll use as examples or as sort of test benches for this, sort of selected on purpose here, are, there are two of them. The first one is DeepClean, which is a network that's designed to do noise regression for gravitational wave data. So its architecture is that of a convolutional autoencoder. So you see the architecture in the top right here, starting with a time series, and it basically uses convolutional layers to sort of shrink the size of this down to some latent space and then expand it back out to predict the noise. So the input data here is data from witness channels, monitoring the instruments and other noise sources, and the output is the predicted noise learned from basically the coupling between these different witness channels as input and the strain data. The architecture has been shown to successfully handle, linear, nonlinear, stationary noise sources. So really the full suite, and to perform basically all the tasks that you desire out of an oh, sorry, hold on one sec. Out of a noise regression algorithm. The other nice thing is that the astrophysical signals here remain unaffected. And so this DeepClean is a really nice algorithm to use here, because it's the kind of thing that you'd like to probably run on top of or in front of almost any detection algorithm, right? You almost certainly want detection algorithms to see cleaned strain data as opposed to uncleaned. And so this is something that sort of belongs in any sort of pipeline, or most pipelines you can think of for detections.
Dylan, if I could abuse my privilege and interrupt.
Yes.
Does this output just the clean data set, or does it also output some characteristics of what was removed?
No, so the output is just the cleaned data. So the input here basically is 21 channels by 8,000 time samples. And then the output is just the predicted noise, basically, for each of those time samples. Okay. But it doesn't give any sort of statement about the source or the type or something like that.
Okay.
Yeah, certainly. I mean, one thing maybe that we may come to is definitely that there are certainly things that you may want to modify about this sort of algorithm, or any noise regression algorithm. And I think that's sort of why I wanted to give that disclaimer at the beginning, that this is not a machine learning talk, is that hopefully by the end, it'll become clear that the exact specifics of the design of these algorithms is maybe sort of a separate problem to the deployment of them. And that's, they both have their own sort of things that you want to keep track of, and that just because you have a solution to one doesn't mean anything really to whether you have a solution to the other. Yeah, so DeepClean is the noise regression or noise removal algorithm that we'll use in this work. The other part is sort of a detection algorithm, and in this case we have an algorithm that we've developed in-house called BBHnet, which is the detection algorithm for binary black hole mergers. It uses as input the cleaned strain data from both detectors. It's got a convolutional architecture sort of similarly to DeepClean, and we plan to release a paper on this. It's not out, but you can see sort of a schematic of what sort of the workflow here might look like with BBHnet and DeepClean. You have some set of channels that come in as input to these DeepClean algorithms that clean the strain data from Hanford and Livingston, and then those clean strain data can, say, both be passed to BBHnet, and you'd want to run this detection, say quickly. And you also sort of separately, maybe you're interested in keeping track of the clean strain data from these two detectors for other algorithms that you're running for bookkeeping purposes, for whatever you're maybe interested in. so then these sort of three things, the two clean strains and the detection sort of score, are all things that you might want out of this sort of end-to-end workflow, as we call it. So this is great. So we have our two algorithms that we're going to use to talk about. We have this sort of complete or end-to-end workflow, as we'll call it. You know, and the reason that we have these algorithms, in addition to many others, is that I think there's been a real revolution and a real sort of increase in interest in deep learning. There's things that are sort of, there's a few reasons for that, or there's many reasons for that probably. One of them is probably that there are now a huge amount of tools that you have that can do deep learning. So this clearly reduces the barrier to entry and these sorts of things. You have multiple different software frameworks that are all capable of doing effective training, of doing effective inference once you have a model. And in addition to the software side, there's emerging and developing hardware that's able to do efficient inference. You know, there's GPUs, which I think most people probably know of, but there's also, you know, specialized hardware from Google, like TPUs. There's FPGAs and ASICs that are being designed. There's really like a wide range of hardware that's being designed for this sort of thing. And all this, I think, combines to give this boom. With that said, it's still a young field, and there's definitely some stumbling blocks here. One really big one, I think, is that there's pretty poor interoperability between different frameworks. You know, if I train a model in TensorFlow, that doesn't mean I can just run the model in PyTorch or run the model in Onyx. And if I train the model in TensorFlow 1, that doesn't even mean I can run it in TensorFlow 2, right? So there's a huge amount of headaches that you can cause yourself, and that can be caused by the fact that there are so many different frameworks and they don't all have a central sort of language that they can necessarily speak, at least yet. The other thing is that if you have a problem and you find a solution, or you find a way to improve some particular workflow that you're dealing with inference, that improvement can be highly framework specific. So, you know, you might figure out a way to make your model run really fast in TensorFlow, but if somebody trains a slightly different one in PyTorch, maybe you have no clue what to do to make it efficient. You know, if I have a solution, it maybe doesn't get translated very well to a different, you know, if somebody changes the architecture, maybe that improvement doesn't translate as well anymore. My improvements might only be applicable to certain hardware types. So there's all sorts of sort of sticking points here that mean that just because I have what I'll call a good algorithm, right? Just because I have an algorithm that does the job I've given it well, doesn't mean I have the actual infrastructure capable of making that a good solution. With all that said, I think that this idea of inference as a service and well-designed inference as a service addresses almost all of these issues in a way that hopefully will become apparent by the end of the talk. So what is inference as a service? Inference as a service is maybe a specific sort of concept under the more sort of general heading of computing as a service, for the special case where the compute that you want to do is inference. The basic idea here is that in a traditional sort of mode of processing, this is, I should maybe caveat this is sort of an LHC type picture with different events, but the sort of logic here holds regardless of what sort of what kind of data you're talking about. In a traditional pipeline, you know, you have some input data, you have some number of threads on your processors, and you have some number of algorithms you want to run on them. You have some number of tasks you want to do on that input before you create the output, and you sort of move on to the next thing. Either you move on to the next, you know, block of either you move on to the next event in LHC physics, or you move on to the next sort of block of time, maybe in gravitational waves, or, you know, whatever this next thing that you want to do is, right? So that's the traditional process, is you have these sort of things, and they're all basically just running on however many threads you have in the CPU. The as a service model says, well, maybe I have some algorithm that actually runs way faster on a GPU, or maybe it doesn't even have to be a GPU. Maybe I have some algorithm that runs way faster in some way, right? Somebody's designed something that allows me to run algorithm 2 quickly. And that's the basic idea here. Well, instead of trying to like integrate this thing, whatever it is, whether it's a GPU, whether it's intelligent, instructions for a CPU, whether it's whatever this optimization is, instead of trying to integrate that into the sort of each processing job, why don't I just separate that out? And then every time that this processing wants to do algorithm 2, it just sends the stuff that algorithm 2 needs to, in this case, the GPU. The GPU runs the algorithm, and then it sends the answer back. And so then, if this algorithm runs quicker on a GPU in this example, right, you can reduce the latency, and you can also start to sort of now intermix these things, and you can get speedups there as well. But that's the basic idea, is that you have this sort of, in this case, the GPU is basically a service that you call on as needed to do a part of the processing. The idea here is that you have then software that's optimized to asynchronously execute these complex workloads. And in inference as a service, this means inference workloads. So this can then be made hardware and framework agnostic, because you can basically obscure all the details of the hardware and the frameworks that actually run these things from the person that's actually doing things. And I'll show how that works. The client, which is basically the thing that's requesting information from the server, basically only needs to know where to send these inputs. They don't need to know details. Again, they don't need to know details about how the models run, and that code that runs that does the actual execution can basically remain separate, and those can be optimized individually. And all clients can then be synchronized to the same versions, and they can get the same kind of speedups and things like that. So I have a little schematic representation of something that you might want to do. Maybe this top box is a set of basically things that you want to do. You have some data that comes in, this X raw. You want to do some pre-processing on it. You want to run your model on it, and then you have some post-processing you want to do, right? And if I wanted to implement this myself in my own sort of pipeline locally, right? Maybe this model function, has to load the model file that I've trained in whatever service, and then it's got to run model.predict if we're in Keras or TensorFlow, and it's got to, it's depending on exactly what kinds of what framework I'm in, I have to write this model function. But I've written this sort of intentionally, but the idea here is that this model function can be anything, right? From my perspective here, if I want to run these things, this model just has to give me the answer. And so whether it does, sort of more what I'll call traditional looking, machine learning ops, like loading models and running predict, or whether it calls some sort of external package that just sends this input X to some IP address and asks for the inference for a particular model, these look the same and they give me the same result. And now I don't have to worry, if I'm the client, I don't have to worry about what's actually happening here. And if the model changes, I don't have to change this file here. And if somebody changes the framework, I don't have to change this. And if somebody finds an optimization, everybody doesn't have to update their code. Only the server has to change, because everybody's just asking the server for this answer. Another nice thing about inference as a service that makes this really convenient is that with containers, you can make this sort of server deployment portable. So you can minimize managing these environment overheads. And if you have, a workload that's variable, right? That doesn't, maybe people request things constantly for a week and then there's nothing. You can very easily sort of scale services to meet the needs of your clients. So we've done a lot of exploration, or inference as a service itself has been explored a lot for LHC and neutrino physics, both in the context of GPUs and FPGAs, with many different models and architectures. So the bottom left here is for ProtoDune, which is a neutrino experiment on GPUs with CNNs. The top right is a small dense network on a GPU for LHC physics, and the bottom right is an FPGA for the same algorithm. All of these demonstrating basically effective speedups of the algorithms with as a service. What I'd like to talk about today is how we've shown that to do this in the context of LIGO, but hopefully in a more generic way. So the sort of first thing to talk about then is how you actually deploy this as a service. What does this actually look like from a design perspective? So again, one of these nice things about inference as a service is that it's not tied to a specific hardware platform or a deployment location. So you can tune this to meet particular needs. So in one sort of vision you might have, maybe you're doing this on the LIGO data grid. So you have some gravitational wave frame files in shared memory. You have some Python process that has to do, load the data, do some pre-processing, request that it does the inference or do the inference, and then do some post-processing, and then it sends that input down sort of downstream. And in this case, you can host the service, or the server itself can be hosted sort of locally to this process, minimizing the amount of overhead you get from data transfer, but you can still get the some nice effects from this kind of thing. But in this case, you can have all these sitting in the same place and just pulling some model from the cloud or some sort of central place so that all these servers get the same model. Alternatively, you can put all this stuff in the cloud if you want to sort of scale this out. And now each of these sort of orange boxes here with the servers, you can imagine having many copies of these. And again, if these are sort of containerized, this is a fairly straightforward thing to do, to sort of just change the number of these there are. And then that means that instead of having one person or one client requesting things, you have a bunch of them, then they all sort of are able to be served effectively. But this being able to sort of move these things around, I think is definitely one of the strengths of as a service and of inference as a service. What we use in the sort of as part of this, part of HERMES and as part of effectively doing as a service is something called the Triton Inference Server. So this is an off-the-shelf inference service, which is maintained by NVIDIA. It's designed for GPUs, so it does very efficient scheduling of GPU resources. It supports multiple framework backends. So this is part of the solution to these sort of framework arguments or disagreements that can happen, is that this sort of central thing here is not, it just needs, it's designed to support as many of these as possible. That's a selling point. And it has pre-built containers, so you don't even have to, there's a lot of sort of management overhead and maintenance there that doesn't have to happen, because you just download the newest Triton container and it does exactly what you need it to do already, basically. And it has a lot of other nice features that relate to versioning and relate to scheduling, so that you get the most out of these servers. And it's separate from the installable client libraries, so that, again, you can get sort of speed ups or modifications to the server that are separate from the client itself. One thing that we definitely take advantage of that I'll just note quickly here is this idea of an ensemble model or ensemble scheduling. So in the simplest case, you have a server and you want it to do a model, the inference for a single model. And that's nice, but in a lot of cases, and in our case here, right, you have multiple models that you perhaps want to do, that you want to run successively in this case. And so Triton supports basically ways to do this sort of thing where you have an inference request come in, you send the input data along with it, and then Triton does all of pre-processing, first inference, second inference, post-processing, and then sends the final result back. And these things can become sort of non-serial. You can have pre-processing inference and then two separate inferences, and then post, these things can get fairly complicated. And this is all supported sort of natively, which is really convenient. So as I mentioned before, this toolkit called HERMES is something that we've designed that intends to basically bring these features of inference as a service to real-time data, essentially. It's built on Triton for the server deployment and management. And while it's designed specifically for gravitational wave data, it's not maybe explicitly useful there, and certainly the ideas behind it are not explicitly useful there. And the code is sort of en route here. So one thing that makes inference on gravitational wave data sort of particularly interesting or unique in a lot of ways is the fact that it's this streaming time series. And that brings with it a lot of sort of interesting constraints and things that you have to sort of deal with. The main one, and the ones that I'll sort of discuss here, is that the inference itself typically happens on sort of a fixed length snapshot of the time series. So in this sort of schematic here, each one of these little sort of tadpoles is the value from a sensor. Maybe it's the strain data at a particular time. It's being sampled at some frequency. And so if I want to run on a fixed length snapshot, maybe that's the blue at one point, and then maybe the next time it's the red. And this thing sort of continues to shift over. And there's multiple things that sort of can change here depending on what you're trying to do, right? You can sample the snapshots at a given rate. In this case, it's every other sort of time sample, but that can be in principle anything. And there's sort of a trade-off here that in a lot of cases you perhaps want the highest sampling rate possible, right? In principle, if you're doing detection and you slide this window too far, you might worry that if the event is happening sort of in the middle of my two snapshots, maybe I'm going to miss it if I slide too quickly. So maybe you want to do this sampling rate as you want to maybe sort of do this sampling as quickly as possible. At the same time, a higher sampling rate means more inferences that you have to do. And that means that you have a higher compute load. And the particularly interesting thing about this sort of time series data is that if the length of the snapshot is large and the sampling rate is large, then the I/O can be enormous. So in this case, if the sampling rate is, the idea here, right, is that if the length of the snapshot is long, then each time series contains a lot of pieces of information that you have to send. And if the sampling rate is large, then you're sending that very, very frequently, and you get a large amount of I/O. So what we've developed is an idea to try to minimize this, basically. And this takes advantage of the fact that, as you probably notice, right, if this blue box here is my sort of first snapshot and the red is the next one I want to do, right? In principle, the blue, because the blue data has already been sent, if I want to do the inference with the red snapshot, I only actually need these two pieces of data to be sent. Everything else has already been sent already. And so what you can do, and what we've done in Triton, is to use something called a snapshotter, as we call it. And the idea here is that you have a model on the server which basically just maintains the state of sort of the current snapshot. So when I send the blue, the snapshotter basically sort of caches each of these points. And then instead of sending the red the next time I want to do an inference, I just send these two sort of new pieces of data. They then get tacked on to the existing. The old ones get bumped out, and then you run this, and then you send this downstream through the ensemble to whatever other models in the pipeline you want to run.
Dylan, if I could, what in terms of the volume, like putting numbers on it, what's the bad case without your snapshotting, and by how much are you improving it in practice in terms of the I/O?
Yeah, so if you had a case where maybe you have a sampling rate of 4,000 hertz, right? And so then if maybe that's the data rate basically, and if you want to do inference at that 4,000 hertz, right, then you're sort of resending. Then the data reduction you get by switching to the snapshotter is 4,000. Basically, it's a 4,000 factor of 4,000 reduction in the data that you send per inference, because you only send one instead of all 4,000 pieces.
So that's a sort of, but this is done at the cost of some sort of processing overhead.
Yes, yeah, and we'll come to the sort of limitations that this does impose. And you are right. It imposes processing overhead. The more tricky thing is that, and this is not maybe something that's permanent, and indeed we've had some discussions about with Triton about whether there might be ways to skirt this issue. Currently, the way that this sort of thing works is that because the state gets maintained on sort of one GPU, it's hard to parallelize this snapshotter in an effective way. So that if doing this like state update, as we call it, is sort of slowing you down, is bottlenecking your inference rate, there's not a whole lot that can be done about that, because there's no way to parallelize it, which is very different from generically any other model. You'd say, well, I'll just make more copies of it. Basically, I'll have it run, in parallel, but you can't quite do that with the snapshotter as it stands. So there are some limitations that this imposes, although we think that these are not sort of permanent technical issues, and that they can be solved. But this does, for most cases, this really does a very good job of reducing the I/O that you deal with, and that's, I mean, that I/O can get quite large if you're not careful. To showcase sort of how effective this is, we have sort of two pipelines and two sort of scenarios that we'll talk about. The first is offline, and the second is online. So in the offline case, this is the case where the data has been collected already, and you want to basically, you want to analyze it. So all the data that you want for this particular processing is already available in some sense, right? It exists on a disk somewhere. It's not to be collected by the experiment. And what that basically means is that in terms of your optimizations, right, you want to maximize the throughput while minimizing the cost to do this. There's not too much of a worry about latency here, in the sense that, at least in terms of latency, that's sort of untied to, I'm talking about latency, sort of a per request latency, not because the total amount of time it takes to process this data is governed by the throughput. So in this scenario, for each server that you have, you assign some number of clients. In this case, we'll call it K. And so then if you have N servers, then each client gets assigned one, N-kth of the total data set. So it gets its own sort of chunk or sequence of the data, and it runs that. And so this is basically a way to parallelize and get around that sort of snapshotter serialness that I discussed earlier. This is sort of a simple way to do that in the offline case. So each one of those clients has its own snapshotted state So it gets sent to the same server every time so that that server can do the correct state update. But this does effectively let you parallelize there. The inference sampling rate here doesn't really have a bearing on the data generation rate. It just determines the number of frames that you need to process for a given length of time. And hopefully that becomes clearer on the following slides. So with this pipeline, or with this sort of offline scenario, we have two pipelines. So the first, we just run deep clean. So we don't run the full end-to-end deep clean plus BBHnet. So we run the Snapshotter and then deep clean. And what we did here was to process roughly a month of O3 data. And I'll try to go over this plot sort of slowly because I think it really very, very clearly illustrates some of the sort of impressive features of inference as a service. So the x-axis here is the time it takes to run per second of data that you're processing. The y-axis then is sort of how many, in how many cases you had that particular time to run per second of data for a given set of, for a bunch of different configurations. So the right is sort of what we call traditional pipeline. So this is on LDG. This is with a GPU. So this doesn't use as a service. This is just, I have a GPU. I write some sort of self-written, but well-written code that does the inference that for deep clean on the GPU. And so this is then the sort of average time to run per second of data for a traditional pipeline is something like, 5 e to the minus 3, give or take, or 5 times 10 to the minus 3 seconds. If you take that same workflow and you switch to inference as a service, you don't use a GPU, you just have a CPU node that does the inference for you with Triton, which is, again, actually fairly straightforward because of all these nice containers that it has. You get essentially immediately a factor of an order of magnitude reduction in the time to run per second of data. If you then take that same inference as a service pipeline and you now start adding GPUs to the server, you get the next 4 colors. So the orange here is 1 server node with 4 GPUs. The blue here is 2 server nodes with 4 GPUs. The green is 4 for a total of 16, and the yellow is 8 server nodes for a total of 32. And you see that as you add GPUs, you basically can continue to reduce the time it takes to run per second of data, almost at will here, to the point where you get to this final configuration. And obviously, I understand that we're comparing apples to apples here, but we're now talking about something that's 3 orders of magnitude faster than the traditional pipeline, and is actually more portable, more transferable, more easily updatable. And even with a much sort of less beefy configuration than the yellow, you still get almost 2 orders of magnitude speed up. So this is really cool. I mean, this is a huge amount of speed up for relatively low cost. To do a real full test of this kind of as a service workflow, we create the end-to-end workflow here. So this then runs deep clean and BBHnet. The basic idea here is that we send as input to this server, we send it all the information to run a deep clean for the Hanford detector, a deep clean for the Livingston detector, and it's then able to run those deep cleans, produce noise estimates, do a noise subtraction of the strains from each, and then use those clean strains to run BBHnet and produce a likelihood estimate for a binary black hole merger. One thing I mean, this is the workflow here. There's multiple different frameworks that we can use here, which again, I think illustrates how sort of useful this ability to just sort of pick and choose where models come from and what form they're in. So the Snapshotter is written is done with TensorFlow. The deep clean models are packaged in a sort of particularly nice format for Triton called TensorRT, and well optimized. And then the noise subtraction and BBHnet are ONNX modules. So we have 3 different frameworks here that are all sort of playing together very nicely. And there's no sort of real issues with doing that. And if one of them changes, that's not a big deal. If all of a sudden there's a BBHnet in TensorFlow, that's not a problem.
Yeah, I'll interject. We have about 15 minutes left.
Okay. So what can we get if we actually run this? You know, how does this actually work in real life? So we ran on about 27 hours of O2 data. And there's a few things that I want to point out. So the results are at the bottom here. The left plot, left sort of subplot here is with a 10 hertz sampling rate. The right is with a 20 hertz sampling rate. So, you know, just double. The x-axis here is the number of clients per server node. And the y-axis is the time to run per second of data. So the sort of a similar thing to this axis here. And then the different colors here are different numbers of GPUs on the server nodes. So the yellow, or the orange here is 2 nodes with 4 GPUs. The blue is 4 nodes with 4 GPUs, and the green are 6 nodes with 4 GPUs. And what you see is that as you increase the number of GPUs, you go from orange to blue to green, you reduce the processing time as expected, basically. So, you know, you cut it in about half by doubling the number of GPUs, and then it goes down by another 50% or so when you increase again. And that's true regardless of the sampling rate. That's true regardless of the number of clients per node, basically. If you then look at the cost of doing this, so now the y-axis here is, instead of the processing time, we have the cost per second of data. If you look at the cost here, you see that regardless of the configuration, you get fairly constant cost with respect to GPU usage. So if you look at each one of the sort of groupings, you know, whether you run with 2 GPUs or 4 GPUs or 6 GPUs, you get basically the same thing. And what that means and what that tells us is that the server is able to efficiently make use of the resources it has, regardless of exactly how many of those resources it has, or what the request rate is, or any of that stuff. This is all basically handled in an efficient way. The other thing to point out is that if you look at these sort of on top of each other, this becomes a little clearer. So if you notice that if you increase the number of clients per node, you do get a reduction in the processing time. So if you look at the first data point here, say for the orange, and then you move to for 2 clients per node, you move to 3 clients per node, you see a reduction. You move to 4 clients per node, you see maybe another reduction, maybe it's the same. And that's true for 10 hertz or 20 hertz. You know, you see this initial reduction, maybe another small reduction, and then you sort of level out. And what that means is that the server's able to maximally perform even as it runs out of resources. And even as you increase past 4 nodes here, or 4 clients per node, you still get to maintain that sort of maximal performance. You don't all of a sudden start bumping into each other. The server is able to handle all these things sort of fully seamlessly. And there's not, there's no like hand tuning here to make each of these points work. This is really basically out of the box. And so it doesn't matter which of these configurations you find yourself in. These tests, if you do the math out, these tests come out to something like 36 clients in the largest case. One of the really nice things about Inference as a Service is that it is very scalable. And so in order to sort of prove this, we used a tool called HEPCloud, or a framework called HEPCloud, which comes from high energy physics, and it's designed for basically sustained high throughput job submission, and in this case, inference using Condor APIs. So we're able to run these really large tests. So the orange here is now 100 clients running with 4 GPUs for the servers. The blue is 1,000 clients with 40 GPUs, and the green is 2,000 clients with 80 GPUs. And then basically what happens is we start each of these 100,000, 2,000 jobs all at once at time 0, and then we just let them run. And you can see that regardless of what particular case we're in here, we're able to basically get fully sustained processing at each of these points until we finish the job. And it doesn't matter exactly what the configuration is, but this works even for these large numbers of requests all at the same time. So this really is a true test of the scalability of this paradigm. So in addition to the offline case, we have the online case. Here, the data, unlike the online or the offline case, is available in real time. So in this case, we want to minimize the sort of per inference latency. We never want any one inference to take too long to come back to us. So here we're basically saying we're running on the shared memory data replay frames, and the inference rate then dictates not the sort of instantaneous data rate, but the average data generation rate, because each of those frames only becomes available sort of in 1 second increments, a second spaced out. Because there's only one data stream here, as I sort of mentioned earlier, that means we only have one snapshotter, and that has some ramifications for what you can do in this case. So the plot here, the x-axis is the sampling rate in Hertz. The y-axis is the latency for that sampling rate, sort of the average latency. So each of these is a distribution here, and then this is the sort of plus and minus 1 sigma in the central values. The blue sort of bars in each of these, or blue parts of the bars, represents the compute latency. So that's basically like the actual inference time. How long does it take to actually do the inference? The orange is what we call queue latency, which is basically how long does it, if I send a request there, how long does it sit around sort of waiting for the resources to become available until it's allowed to sort of enter the inference stage and actually run. And what you see is that at low sampling rates, so when you don't have too many requests, you get sort of an average, per request latency of about a millisecond. And you don't really see any increase in that if you move from, say, 600 Hertz to 800, because both of these can easily be sustained by the server in this case. At 1,000, you start to see some evidence of queue buildup. And as you increase past 1,000 Hertz, you see that now all of a sudden, instead of your latency being basically fully dominated by the inference, you now start to build up long queue times in some cases, waiting for these requests before they actually get processed, because the server isn't able to run fast enough to keep up with the request rate. And so then, if you keep increasing the sampling rate, you keep increasing the amount of queue latency. Once you start to be dominated by the queue latency, you do get some improvements from having more GPUs. So each of these, each of the 3 bars here, the left one is a 1 GPU server, the middle one is 2 GPUs, and the right one is 4. So you do get some improvement by moving to more GPUs, but because in a lot of cases you're bottlenecked here by the sort of a serial updating step in the Snapshotter, you don't get as much of an improvement with the multiple GPUs. And this is something that we are working to optimize. One other comment, and this maybe comes to your first question about deep clean, or maybe sort of is related to it in some sense, is that there's multiple ways you could think to use the deep clean output. So the deep clean output is just the sort of noise removed time series. You could think about it in perhaps a fully online case where you just, the new information that you send to deep clean, you basically take that time that you run deep clean, you take that noise prediction for those time series, and you use those as the noise removed estimate. This is what we call a fully online inference scheme, and this has some negative impacts on the PSD. It turns out if you take multiple iterations of deep clean over sort of successive inference requests and you aggregate them, you can remove a lot of this. So in this case, so 0 seconds is basically what we call the fully online. So you basically take no additional, you take no overlap, you take no amount of aggregation, and then the dashed orange and the cyan are cases where you take now basically half a second of aggregation to get the estimate for a particular time. In this case, it's 0.75 seconds. And you can see that once you get to 0.75 seconds, you can basically almost exactly reproduce what we call the offline case, which is where you take every single deep clean estimate possible on a given time sample and use that for the noise estimate. So this means that if you really wanted to run this online pipeline, you wanted with the current deep clean model, you'd need to wait about 3/4 of a second in order to get reliable noise estimates to do downstream processing, et cetera. That's something we think could be improved with some modified training and things like that, but that's sort of a limitation of the current algorithm that in principle you might want to update. But again, these are all things that you can, that's sort of a model adjustment side as opposed to the sort of infrastructure that I've been talking about. So I'm almost done here. So the HERMES itself and this whole framework here is intentionally been designed to be generic and open source. Obviously, the use case that we've discussed here, that we've shown here, is for gravitational wave data. But that doesn't mean that this is only useful for LIGO or only useful in the cases that we've shown. I mean, the real idea here and the real usefulness and meaningfulness of, I think, what's of HERMES is that basically any kind of readout in principle can benefit, I think, from the inference as a service paradigm. And certainly other astronomical readouts can definitely benefit in very similar ways. They have some similar sort of latency and data rate requirements to LIGO, and in principle, they can all benefit from very similar things. So inference as a service really opens up a lot of possibilities here. And just to close here, I thought I would just flash this sort of idea that I think once you start to adopt this as a service thing, you start to open up a lot of sort of clever ways to use inference in cases that might have been difficult previously. So, this is a sort of online deployment you might think of for doing deep clean basically in live time, where you'd have a server sitting at each of the two sites. You'd have a central model of repositories that you can both sort of send to from a development server. So anytime you want to update it, it can be, you can send sort of, you can send new models there with some sort of validation steps. That validation can be run sort of as a service. and then the models themselves can be run as a service at the two sites to do the noise subtraction. So in conclusion, I think designing ML algorithms is really only one particular part of the work required to sort of actually use ML. I think efficient and straightforward deployment of those algorithms is equally as important as the actual design of them. And what we'd like to propose here, and what we think is sort of right here, is a paradigm shift in how people think about ML inference in a lot of different places, but in this particular case, we think for gravitational wave data. And the idea with HERMES is to provide the tools to make this possible for real-time applications in a way that's scalable, efficient, generic, easy, fast. And I think we've successfully shown that this is performant both for offline data analysis and all the ways that that's useful, as well as real time. And by that, I mean something like MMA follow-up. So thank you very much.
Thanks very much, Dylan. And does anyone have any questions? And while perhaps people are thinking of questions. So I guess the online case does lend itself maybe to having the specialized hardware next to the experiment. But presumably with the offline, as long as you can secure your data, it would probably be more cost effective to have it in cloud, because you go through the data so fast, you don't need to have something up all of the time.
Right. Yeah, I think that's definitely true. And then that's definitely one of the reasons that having this be scalable and containerizable in the ways that it is really nice. You can expand the sort of pool of resources that you use to do to process a replay so that it can do it as quickly as possible, and then scale it back down when you don't need as many resources in sort of day to day.
Right, and my other sort of connected question is, even with the online case, presumably, you're doing this stuff at two sites. You then have to combine it somehow. So you do have a message passing issue at some stage, where you want it to be performant, and you want to secure the information because it's proprietary at this point. Yeah.
If you sort of see this is only for deep clean, but yeah, like you said, you sort of have to send it. I mean, you could send one of them to the other one, but you probably have some, it's probably more intelligent maybe to send it to some central place to do this. Although there's a lot of freedom here, I think, because of the way that this is all designed. But yeah, I think you're totally right.
Okay, yeah. Okay, so there's one other thing, which is it's not a question / comment from me. It came from a private comment to me. Are you familiar with the use of FuncX, sort of the Python library FuncX, for managing this sort of thing in HEP? There's a paper that went on the archive in March called Distributed Statistical Inference with PyHF enabled through FuncX. But just to sort of marshal all this stuff, I think they're talking about function as a service rather than inference as a service, but they seem very similar to them.
Yeah, I think there's, so I have seen FuncX, and I think that, yeah, this sort of as a service, generic as a service idea, I think is definitely one that's gaining popularity. And I think it's a good thing. I think this is it's a different way of thinking about these sorts of problems. It's different than just saying, I'm going to buy a bunch of GPUs for my personal stuff. But I think there's a lot of reasons that this is the right way to go about doing things.
Right. And if I can just have a quick plug for SCiMMA's work, one of the things we're working on with Hopscotch and building an ecosystem on that is, in fact, having what we call an analysis platform that might be running on, say, what are called Exceed resources, or on some other supercomputer that has GPUs enabled, where you could message into Hopscotch. It would then be referred to the service where the hardware lives, and then come back out that way. So that would be a little higher latency than right next to the instrument. But I think in general, this sort of thing is the way to go going forward, which is why we've asked you to come back to give this talk. Okay, so we are a little past time. This talk will be available on YouTube sometime this evening, and I'll send a link to the Google group. But I'd like to thank Dylan again for coming and giving this talk, and I hope we get to work together in future as we both develop our own solutions.
Yeah, definitely. Thank you very much for having me.